Going to look now at roots of quadratics when we are dealing with complex numbers. So let's consider this equation here. We want to solve it. So x squared minus 4x plus 5 is equal to 0. So if we were to factorise that, it would factorise into x. That would become x plus 5 and x minus 1 is equal to 0. And then its roots would be x is negative 5 and x is positive 1. So let's have a look at the roots of our equation and the factorised form. So we can see here that we have a plus 5, the root is minus 5. Minus 1 here, the root is plus 1. We should be quite familiar with that when we're solving equations. If alpha and beta are the roots of a quadratic, then if it's in this form here, x squared plus bx plus c, then we know it's going to factorise into this, where alpha and beta are the roots of our equation. So if we look at it for this one, if we said that alpha was negative 5 and beta was 1, we can see that when it factorises, alpha is negative 5, so minus alpha will be positive 5, beta is 1, negative beta would be negative 1. So that we already know that, it's just putting it in that form there. And then what we can do is we can expand this out. We expand that out, and it's going to give us an alternate way of writing quadratics out in relation to their roots. So if we expand that out, we'll get x squared, we'll get a minus beta x, we'll get a minus alpha x, and then we'll get a plus alpha beta at the end. And then if we just clean that up a little bit, we'll get x squared here, and take the minus out here, make this alpha plus beta. I'm just going to make it like that, even though we've written it minus beta minus alpha, the order doesn't really matter. Then put the x on the outside plus alpha beta. So we can write all our quadratics in the form x squared plus bx plus c in this form here as well. I'm going to write it in this form because it helps us when our roots are complex for our quadratics. So say, for example, I have a quadratic and one of my roots is 3 plus 4i. The other root is simply just going to be its complex conjugate, 3 minus 4i. And we'll have a look now at a proof which shows us why that is the case, and it involves this form here. So let's have a look at how we can prove that. So I want to prove that if our roots are complex, they're simply going to be the complex conjugates of each other. So if I first will start with the quadratic formula. So this is our quadratic formula as we know it. So let's just split that up. Square root bit on its own, because that's the bit which gives us our imaginary part. So we end up with this. Now let's say I wanted to take an I out of here. B squared minus 4ac will be the same thing as minus 1 multiplied by 4ac minus b squared. They will be the same thing, it just swaps the sign around. And what that means is I can then take an I out there, because what I can do then is I can rewrite that as, so I can write it like that, and then we know this root negative 1, we can just write then as an I. So we have there now our roots of our solution. This bit is going to be the real part, and then this bit here is going to be our imaginary part. And we can see that the real part stays the same, the imaginary part is plus minus, so that would give us a complex conjugate, because the real bit is the same, the imaginary bit, the sign changes. We can also prove that algebraically using this here, which we derived up here. alpha and beta are the roots of our equation, and if we expand it, it looks something like this. So let's say that alpha and beta are both complex numbers. So if we say that alpha is a1 plus b1i, and we're going to say that beta is a2 plus b2i. If we expand this out here, we can see that the coefficient of x is minus alpha plus beta, and the number here is alpha beta. So if we want both of these parts to be real in our quadratic, alpha plus beta has to be real, and alpha beta has to be real. So we've got values here for now alpha and beta in terms of a and b. Let's work out what those things are. So if we do alpha beta, so that would be a1 plus b1i multiplied by a2 plus b2i. So let's expand that out. So I get this when I expand it out. And if we just clean that up a little bit, we are going to get this. So we're going to group the real parts and the imaginary parts together. So we'll get a1, a2, and then here this b1, b2 will become minus b1, b2, and then we have plus alpha plus a1, b2 plus a2, b1i. And I've done all that to say, well, I know that alpha beta has to be real. Therefore, any bit that's imaginary must equal 0. So that gives us this thing here. So a1, b2 plus a2, b1 must equal 0. So we know this. Then let's have a look at what alpha plus beta would be. So that's just going to be a1 plus b1i plus a2 plus b2i. So again, group the real and imaginary parts. So we have a1 plus a2 being my real part, and then b1 plus b2i being my imaginary part. And again, we know the imaginary part has to be 0 because alpha and beta has to be real if we want these two numbers in our quadratic to be real. So that gives us this thing here, that b1 plus b2 must equal 0. Work with this then. So let's have a look at this. So if we do this and move that b2 to the side, we'll get that b1 is equal to negative b2. Let's now take this result and put it into here. So I'm going to replace my b1 with a minus b2. So I'm going to have a1, b2, and then that's going to be minus a2, b2 is equal to 0. Let's factorise out that b2, which is a1 minus a2, in the bracket. So for that to equal 0, b2 has to be 0, or this bit here has to equal 0, which must mean that a1 is equal to a2. And if we go back to what alpha and beta were, so alpha was a1 plus b1i, and beta was a2 plus b2i. So we've already said that b1 we replace with minus b2 or vice versa, and a1 and a2 are the same. So it's going to look something like this. So alpha can stay as it is, and then beta, we know that a2 is the same thing as a1, and then b2 is the same thing as minus b1. And that proves that they are complex conjugates because the real part is the same, the imaginary part, same value but different sign. It says alpha is 7 plus 2i, and that is a root of a quadratic equation with real coefficients. And then part A is state the value of the other root beta, and then part B is find what our quadratic equation is. So part A is really straightforward. We know if one of our roots is a complex number, The other root is just going to be its complex conjugate, and we've proved that before. So beta is 7 minus 2i. Now, for part B, there are two ways we can do it. One is slightly quicker than the other. So the first one we can do is we can go back to what we said at the start, and we can say that z minus alpha, z minus beta will be equal to 0, and we can factorize it like this because we know our roots, alpha and beta, it's just minus that within our bracket. So we can put alpha and beta in there, and then we can expand all that out. So let's do that to start with. So 7 minus 7 minus 2i, and then we have beta, which is z minus 7 plus 2i, like that. So we then just need to expand that out. So there are multiple ways to do this. I'm actually just going to do the grid method, because when we've got like 3 terms like this, I think that's just going to be easier for me to do. So let's do that. So we're going to end up with z squared here, minus 7z here, and then we're going to get minus 2zi here. Then we'll end up with minus 7z, then plus 49, and then we'll end up with 14i here. Then we'll end up with 2i times by z, so that'll be 2zi. And then we'll end up with minus 14i, and then we'll end up with minus 4i squared. So then let's now group all that together. So we have our z squared. Then let's get our z. So we have a minus 7z and a minus 7z, so that'll be minus 14z. And then we have a 2zi and a minus 2zi, so that cancels out, which is what we want because we want to make sure that we have real coefficients. We shouldn't have anything imaginary there. Then we have our 14i and a minus 14i, that'll cancel out. And then we've got a 49 and the minus 4i squared. Remember, I is just negative 1, so that whole thing just becomes 4. So we have 49 plus 4, which would give me 53. And that is our quadratic. The other shorthand method we can do is use the expansion of this. So instead of that, we can say, well, if I expand that out, that's the same thing as 7 minus alpha plus beta z plus alpha beta is equal to 0. And then all I need to do then is find what alpha plus beta is and then find what alpha beta is, and that will give me my coefficients. So alpha plus beta is just going to be 7 plus 2i plus 7 minus 2i. The 2i's cancel out, giving us our 14. So that's our coefficient of z. And then alpha beta is going to be z plus 2i, z minus 2i. So that'll give us 49 even, if we multiply it. And then we know that i's are going to cancel out, because we're going to get a plus 14i and a minus 14i, and then we'll get minus 4i squared, which we know is just going to be positive 4. So that is going to give us 53. So you can see there we get the exact same numbers. This is negative 14. Remember, it's negative alpha plus beta, which is coefficient of z. So put the 14 in there. It's negative 14. And then alpha beta is 53. So we get the same thing. Z squared minus 14z plus 53. That 2 minus 4i is the root of this equation here. Find the other root and find p and q. So it's a quadratic, and we know one of the roots is complex, so the other root is simply going to be its complex conjugate, so it will be 2 plus 4i. And then find p and q. Z squared minus alpha plus beta z plus alpha beta is equal to 0. So let's just put in alpha and beta into there. So this is definitely the quicker way, but if you can't remember that, either expand it or you can just put it into the double brackets and expand that out. So we'll end up with 2 minus 4i plus 2 plus 4i. The 4i's cancel out, giving us alpha plus beta of 4. And then alpha beta is just going to be 2 minus 4i multiplied by 2 plus 4i. That's going to get us 4 with the i's cancelling out, and then we'll get minus 16i squared, which is just positive 16, which will be 20. And then let's just put it in the form of the quadratic, so it will be z squared minus 4z plus 20 is equal to 0.